Okay, as promised, I'd like to take a couple of minutes to work through two z-test problems with you. It's important, though, I really want to emphasize, it's important that you understand how these tests work. It's important that you understand the underlying logic of why we do tests like this in general. Part of this depends upon a clear understanding of the sampling distribution, excuse me, what it is and how it works. Because simply being able to solve these problems by plugging values into equations is just not going to cut it for you in this class. So let's start out with a simple example. As in every problem, we'll begin by stating a hypothesis. H0, or our null hypothesis, is that this sample that we're going to do something to has a mean equal to the population mean, which in this case is going to be 500. H1, our alternative hypothesis, in this case we have some theoretical reason to believe that our sample is going to score better than our population. So we're going to use that greater than sign. We're hypothesizing here that the folks that got the treatment, the folks in our sample, are overall are going to produce a higher mean score on whatever this is than our population. All right, let's get some values down here to start to work with. Mu, of course, equals 500. This data set happens to have a standard deviation, if I can find it here, a standard deviation of 100. We're going to select a sample of size 20. And as it turned out, after our treatment, our sample had a score of 562. Let's set an alpha level equal to 0.05, and let's get started. The first thing that we always want to do is draw out this little sketch of what the problem is asking us for. So I'll do my best to draw it out there. Not the greatest, but good enough. So 500 is our mean, or in z-score terms, 0 is our mean. And we're looking for, this is a one-tailed test because we have this greater than sign. So it's a one-tailed test, and we're proposing that our sample score will be higher than the mean. So we're going to be out here someplace. What we're going to need to find using our calculator is what that critical value for z will be. Okay, well, we'll get to that in a minute. All right, so how do we solve a problem like this? Well, we need to convert these scores to z-scores. I'll give you the general formula. Our sample mean minus our population mean divided by our standard error is going to give us the z-score, our computed z-score. The standard error, of course, is equal to the standard deviation for the population divided by the square root of the sample size. Okay, so can do some calculating now. Our standard error is going to equal, what is it, 100 over our sample size, which is 20. And if you do that little bit of arithmetic, you're going to come out with a value of 22.36 or thereabouts. All right, so we have the denominator now of our z equation, and let's finish up by computing the numerator. So that's 562 minus 500 divided by 22.36. Okay, and if you do that calculation, you're going to get a z-score of 2.77. So now the question is, what is the critical value that we need in order to reject a null hypothesis? What is the value that has such a low probability of occurring purely by chance that we feel confident in rejecting that null hypothesis? Well, to do that, we can look at the z-score calculator, and I happen to have that over here if it will come up. Oh, Control V for paste, and there we go. All right, and let's take a look at what's going on here. The first thing that I want you to notice is that the range that is selected here, the range that's shaded, matches the range which is shaded in our diagram. So we know that we've set the calculator up correctly. Check a few other things. We have a normal distribution, that's right. You'll be using, by the way, the t distribution and then the f distribution. So the calculator works the same, well, it works a little bit differently, but you'll click this drop down for the t and then for the f distribution. For right now, just the normal or z distribution is what we need. Again, we're working with a z-score. Every mean of a z distribution is 0, and the mean of every the standard deviation of a z distribution is 1. So that's correct, and that's correct. And then we're working with alpha equals 0.05. So I entered alpha equals 0.05 over here. That gives me then over here my critical value for z. Any value above 1.6449 is I'll reject. So I'll just put in 1.6449 over here so we know what we're talking about. 1.6449. Our z value is 2.77. It's way out here someplace. I don't know where it'll be, but it's way out here someplace. So in this instance, we can reject the null hypothesis. Okay, so that's how you'd go about solving a one-tailed test. Let's move on now to take a look at how you would solve a two-tailed test. Okay, for a two-tailed test, let's look at a problem that looks like this one. Again, we'll start out with our null hypothesis, the state of the world. And in this case, we have a sample. And assuming that whatever treatment we give to the sample, whatever we do to the sample, the mean for that sample is not going to differ from our population mean of 400. Our alternative hypothesis, H1, in this case, is going to be that we don't know what the sample mean will be, except that we're hypothesizing, we're proposing that it will be something other than 400. Whatever we did to these folks in our sample group, they're going to wind up having a score, a mean score in the sample group that is not equal to 400. All right, so let's get some numbers in here now, like we just did. Mu, of course, our population mean is 400. Our population standard deviation equals 40. We'll draw a sample of n equals 36. And after treatment, it turned out that our sample had a score on whatever instrument we used of 392. Okay, as before, we'll set alpha equals to 0.05. Okay, and again, we'll draw that diagram. Now in this case, things are going to work out a little bit differently. Oops. This is kind of slippery, this tablet I'm writing on. Well, that's the best I can do. Okay, so we'll put 400 over here, but remember we're operating on a z-scale, so we'll put 0 just to indicate that. Now, we don't know whether or not our sample mean will be below or above 400, so we need to take both possibilities into account. Our alpha level is 0.05. So what we have to do in a two-tailed test is divide that 0.05 into both the lower tail and the upper tail, because we'll reject the null hypothesis if we get a computed z-score that's somewhere over here, or a computed z-score that's somewhere over here, right? So in a two-tailed test, we divide that 0.05 into 0.025 on the lower end and 0.025 on the upper end, okay? Obviously, 0.025 plus 0.025 equals this 0.05. So we're distributing that probability in either tail. Okay, let's do some computations. I won't bother to write out the formula. Well, I will write it out. What the heck? Sample minus the population mean divided by the standard error. Okay, so the first thing we need to do is calculate that standard error. In this case, that's going to be 40, our population standard deviation, divided by the square root of our sample size, or 36. And this, once you do the arithmetic, you'll see is going to equal 6.67. Okay, so now we have what we need to compute the z-score for this problem. Z equals 392, I think, yeah, 392 minus 400 divided by 6.67. So that's going to be 8. 392 minus 400 is negative 8. Negative 8 divided by 6.67. And that equals about 1.20. Okay, so now we have our computed value for z. What's the critical value for z? Well, again, we go to our calculator and paste in. I'm going to move it up here so we can compare. Paste it in over here. And you'll see that I've set the calculator up now with both tails, with the both tails option. And our diagram that the calculator produces looks just like the one that we produced, so we know we set the problem up correctly. Again, we've checked the normal distribution, 0 for the mean for the z distribution, 1 for the standard deviation of the z distribution. We enter that 0.05 alpha level over here, and it gives us the lower boundary and the upper boundary. I'll write those in. That's going to be negative 1.96 or positive 1.96. Any z value that we calculate that's either below negative 1.96 or above positive 1.96 will reject the null hypothesis. In this case, however, as you can see, we have a calculated z value of 1.20. So we're somewhere, actually negative 1.20, sorry about that, negative 1.20. So we're somewhere in this region. And in this region, well, again, just by convention, we're not going to reject, because there's a reasonable possibility that any sample we could draw, whether or not it was of treated folks that were treated in our experiment or folks that weren't treated, there's a reasonable chance that that any sample would have gotten a z value of 1.20. So in this case, we failed to reject the null hypothesis. Okay, again, let me emphasize that it is critical that you understand not just how to calculate these problems, but what you're actually doing. What is a two-tailed test? What is a one-tailed test? Why would we use one test versus the other test? Also, what influences the value of the z-score? Well, you can see it's going to be the computed the sample mean and the population mean, but we don't really have any control over that. That's just the state of the world. There's nothing we can do about that. Not much we can do about the variance, at least not in an introductory statistics course. We can change the sample size. If we make the sample size higher, maybe we'll wind up rejecting. Don't know. We have to be careful. We don't want to go too high, because if we go too high, then we might just reject when we shouldn't have rejected, and that's a type 1 error. Okay? So it's the sample size for right now, and also the alpha level. The smaller the alpha level, right? The smaller the alpha level, the smaller on this end, or the larger on this end, the critical value for z will be, right? In this case, 0.05, you're probably not going to get an alpha level that's much higher than that. But in the other problem, with an alpha level of 0.01, I'm not sure whether we would have rejected or not. So bear in mind, again, what we're doing, what's the logic behind these procedures, and what can we do as researchers to find an effect if there is an effect, and not find an effect if there in fact is not an effect. And for that, you'd have to go back to the video on sampling distribution, and of course the video that it talks about type 1 and type 2 errors. Okay, I hope that you found this helpful. Oh, sorry, let me show you one more thing. We also want to compute Cohen's d, Now, it doesn't make a lot of sense to compute Cohen's d in this instance. Why? Because our results are not statistically significant, so we wouldn't bother trying to find out the effect size, the magnitude of the effect in relative terms, if the test of statistical significance doesn't show that there is an effect. So let me erase this here if I can, and let me go back for a minute to the previous problem if I can. Not going to make it easy. We'll do it this way. I think that's probably all the space. We're going to need actually less space than that. So Cohen's d tells us whether or not a statistically significant effect is in fact meaningful. All right? Computing Cohen's d is very easy. D equals the mean differences, in this case 562 minus 500, divided by not the standard error, but simply the standard deviation for the population, which in this case is 100. So we have 562 minus 500, and that, of course, is going to, let's see, did I calculate this out already? I've got to take a look. Yes, I did. That's going to give us 62 over 100, and that, of course, equals 0.62. So 0.62, as I mentioned in class and as you described in your book, is considered a moderate to a strong effect. According to Cohen, who developed this approach, a value of d of around 0.2, small or minor effect. A value of around 0.4, a moderate effect, and a value of let's say 0.8, a strong effect. You might want to check these numbers by what they give you in the book. These are really rules of thumb. This is not a hard and fast mathematical statement. This stuff in here is not, it's not mathematical. It's really just sort of by convention. So you might want to double check in the book to make sure that I'm giving you these correctly. But that's how you would calculate Cohen's d. And remember, you'd only calculate Cohen's d for an experiment that proved to be statistically significant. Okay, we'll leave it there.